Thank you, Chairman, and thank you very much, Sergio, for inviting me to this workshop and giving me a chance to talk about nonlinear system identification and nonsymmetric Riccati equation. This is a benchmark problem for a CICID year 2009. Probably the chairman knows very well about this problem. About 10 years ago, I was a newcomer to the nonlinear system identification area. So I was looking for a good nonlinear system identification problem to solve. So I thought that this was very nice because there are real data was supplied, and also there are some instructions about the experimental setup. So we presented a paper in this workshop, in this symposium, but our results was not very good at that time. So after the symposium, we continued study of this Wiener-Hammerstein system. This is probably many people will know that this system has two linear subsystems, and one nonlinearity is in between the two linear systems. So this part is called Wiener system, and this part is Hammerstein system. So this is called the Wiener-Hammerstein system. And after a long time, the simulations and the trial and error, we arrived at a good way. We find a good way of solving this problem. And also motivated by partitioning approach, probably some of you know. We wrote two papers. This first one is the updated version of the paper presented at the symposium. Second one is the MIM or extension of the first paper. Since our approach is based on the partitioning, so we have two steps in identification. The first step is initialization. Initialization step, we generate good initial state estimates for optimization. And optimization for each initial estimate, this OI model is optimized by using a gradient method. Of course, the criteria is the output error, of output. And so we need a good, and also, this function is really non-convex, so that we need a good initial estimate for success in identification. And then the best Wiener-Hammerstein model with the minimum mean square error is selected. But in this talk, I just discussed the first stage only. In other words, the estimation of best linear model and the allocation of pole of the best linear model between two linear subsystems by using state space technique. This is a pole allocation or a spectral factorization that arises in nonlinear system identification. This is the content of my talk. First part is the identification of best linear model, and the second part is this allocation, that state space model and nonsymmetric ARE. And I just show you the benchmark model. Okay, again, this is the Wiener-Hammerstein system. We need some assumptions. Assumption is rather standard. Input and output Gaussian process is really needed, because otherwise the whole procedure collapses. So input should be Gaussian, and G1, G2 are stable and have no pole-zero cancellation. And variance of the output or nonlinearity are finite. Then all the variables here are second-order stationary process, so that we can define the covariance function. This is the cross covariance function. Also, we can define an autocovariance function, and so forth. First lemma is for Gaussian input, the exact, this is important, exact covariance function or input out cross covariance function is given by this equation. This is the cross covariance. And G1, G2 are the impulse response sequence. and RUU is the input covariance function. And FE here is the equivalent gain. Equivalent gain is well known for many years, very old stuff. And actually, in my department, in my lab of Professor Sarai, they studied a lot about using this equivalent gain technique to analyze, the nonlinear feedback system. So we know this equivalent linearization very well, but this relation itself comes from the old paper, well-known old paper, Busgan. Both are from MIT, but unfortunately, in my department lab, we didn't know this result for many years. So I noticed these results rather recently. And this relation was already used in identification of Wiener-Hammerstein system in 80s by using in these, for example, in these papers. Okay. And, but we reinterpret this equation by using orthogonal projection. Equation 1 is equivalent to this one. We define G y dt, yt minus yt is orthogonal to ut minus tau. If we multiply two sides and take an expectation, we get recover the equation 1. So that, and also PARP denotes orthogonality. And this technique is very often used by Akaike's paper in stochastic realization. So I use this. And now we define the span of the pulse impulse. Then we see that YD here belongs to UT minus. And also the difference is orthogonal to the pulse impulse, so that YD should be orthogonal projection of YT onto the space, the pulse space. So we write it this way. Of course, tau runs from minus infinity to infinity, but this is a causal function, so that we can express it this way. So, summarizing, suppose that the inputs are Gaussian, then YD is the best linear approximation of YT based on the pulse impulse. Also, YD here is a linear least square estimate of YT based on UT minus. And also this function minimizes this criteria, of course. Yeah, this problem is studied by this paper in the framework of classical Wiener theory in frequency domain. And the best linear model is expressed in this way, and the composition of three transfer function or matrix. And so we can identify the state space model of this by using unfortunately our method or PI models. The reason is probably I don't skip the reason why this technique is good for in this case. I just say that the ORT is compatible with the OE model, so that if the system is linear, there are much difference. But if it is non-linear, there are some differences. Numerical comparison is given in the first paper, and the theoretical consideration is given in the second paper. And so we come up with the polynomial factorization, define the denominator polynomials of these transfer function, phi d, phi 1, phi 2. Then we have this because we don't have the positive cancellation, so that we have this. So we have a factorization problem to find this realizable phi 1, phi 2, given this. N1, N2 is assumed known. N1, N2 is the dimension of the linear transfer functions. And realizable means that phi 1, phi 2 should be a real polynomial. This is note. if f is linear, then this factorization problem doesn't arise. Because if we change the linear element, there's no change in the input-output relation. So that if system is linear, this problem doesn't arise. And also in this talk, we consider only the partition of poles only, but the partition of zero is also possible if this exists. So the transfer function is bilinear, biproper. If we look at the process control system, very often we don't have this inverse, so that we only consider the poles case. If the system is biproper, then we can do factorization of the zeros, of course. So we come to the second step, allocation of poles or best linear model. G1 and G2 are defined in this way. This notation is very familiar in the days of H infinity. And this should be minimal. And then the product of three elements gives in a bar B bar C bar D bar. And this is easy computed. Now, here we assume that linear model is given. Variables without any subscript or superscript this is computed by given data. And if we use some hack here, it complicates the notation, so I just simply write it in this way. And the two realization, this is the obtained identification result. And this is a true system. Two are input-output equivalent, approximately. Hence, there exists a similarity transformation T0 satisfying this condition, of course. T0 is not unknown, of course. So the next step is to find the similarity transformations that transforms A into a block upper triangular form, which is similar to this one. This is a true A matrix. So now we introduce a nonsymmetric ARE. Partition is given. We use a superscript to denote this is the given data computed by using real data using subspace method. And 1 and 2, as I mentioned before, this is the order of the transfer functions on partition and define a nonsymmetric ARE. This is, if the A matrix happens to be the Hamiltonian, then we have this well-known Riccati equation for regulator system or continuous time regulator system. And this nonsymmetric ARE, I'm not very familiar with this one, but these equations are studied in dynamic Nash games with models in twin theory and transport theory. Probably this is a good survey paper that appears in linear algebra applications. And Poloni here is the PhD thesis at PISA, mathematics department. Okay. And by using, defining this similarity transformation, we compute this one. This red equal means actually this should be similar. But as I mentioned before, these variables with superscripts are already given. And we want to find the variable that with the subscript, we want to know it. So that without loss of generality, we put this in equal. Generally speaking, this should be similar. So eventually we have this equality here. So in summary, similarity transformation gives the A1, C1, A2, B2. remaining parameters are independent of x. In fact, we have this kind of equation. Right-hand side, given data, given from the data. The right-hand side members, we want to find it. F is the equivalent gain, but this guy can be assumed to be 1, which does also generality. So now we have the initialization of this form. A1, A2, C1, C2, B2 are determined by solution of the non-symmetric ARE. But we don't, assuming that the identification results are very nice, so that we do not optimize these parameters. Remaining parameters are optimized together with the parameters that appears in base function expansions alpha here. So we need some initial conditions for these parameters. So this is a expression I've shown in the last slide. And this is a given from the data. So we take SVD. So rank 1 approximation we can get. But there are also, redundancy or uncertainty in defining B1, D2, B1, D1, C2. And the initial estimate alpha is obtained by solving a simpler least square problem, but this is omitted. I just remind you that this is well-known eigenvalue-eigenvector method to compute the solution of Riccati equation. But this classical paper already includes the solution of this non-symmetric ARE. And this supposes that the eigenvalues of eigenvalues are distinct. If there is a duplicate eigenvalues, then a sure method. Actually, this paper title contains sure method. So these are the eigenvectors associated with lambda I. And this is the set of eigenvalues, and one set of eigenvalues. This is a complement. And S ranks go 1 to rho. Rho is the possible partition, number of possible partitions. Number possible means a realizable partition. And this is, roughly speaking, the number of real solutions of this. So arranging the eigenvectors in this way, and if the determinant is not non-zero, then we have the solution of this in this way. And this is a feedback matrix whose eigenvalues belong to this S1. And yeah, we use this technique. This is the example, a very simple example. I pick up this example, but I compute, I surprised that these eigenvalues is located outside the unit circle, so that this example is not good for our problem. But anyway, number of partitions, possible partitions are 2, only 2, so that delta 1, delta 2. And arranging for delta 1, arranging this way, we can find this way. This is a solution, and this is a feedback matrix. And our experience shows that we never encounter a case where the U is singular. U is singular. U always non-singular. Maybe there exists some singular case. Okay, so this is a procedure of total identification, but I skip this one. I don't need it. I just show you the benchmark model of the result. This is the benchmark model. Probably many of you know this. The linear system, nonlinearity, designed by a circuit, and this is the linear system. This is the input. This is the output. This is the distribution of the input. This is the distribution of the output. Input distribution is really the Gaussian, but also output distribution looks Gaussian. But if you look at carefully, this is this is some skewed because nonlinearity is not symmetric. And this is the result of the identification of the base linear model. This is a pole. The number of data is 90,000. N is 6. And the SN ratio output is 70 dB. So that I guess the data is really noise-free, I guess, noise-free. So that I think this is very good result. Now, so that computing eigenvalues and counting the possible partitions. And just note, if the eigenvalues are all real, then we have 20 cases. So this is the optimization results by taking advantage of the separable least squares. Alpha is eliminated in the optimization. And so we optimize in 6-dimensional space and 4 cases. So the black one gives the best one. So, the poles are separated in this way. And this is the body plot of the gain two linear system. We can adjust this gain a little bit, but this is the result I got without any modifications. And the nonlinear parameter that express the nonlinearity is recovered from this. I didn't mention anything about theta hat. This is a kind of regression matrix. And nonlinearities. 9 parameters used for. Actually, we use a Legendre polynomial rather than standard polynomial. Okay, this is the conclusion of my talk. Under Gaussian assumption, otherwise it's no good. Under Gaussian assumption, it has been shown that how the technique of linear systems are used in initialization step of identification of Wiener-Hammerstein system. In particular, Nonsymmetric ARE plays an important role in the allocation of state space, in state space. I want to say just a few words about this contains a Japanese or a Chinese character, so that probably it's very difficult to explain. But Sergio, I wish a happy 7th and celebrate you, Koki. Koki in Japan we call Koki, the 70 years old. And this comes from the line of poem by Tohru. It's old person here, many years ago. This is a very, very famous Chinese poet of Tang Dynasty. We learned this Tohru and also Lin Bai, two great Chinese poets in high school days. And here, this is written in a horizontal way, but actually we write in this vertical way. This means it look like lambda, but this is man, standing probably in this way. And this means they are life or birth or alive or something like that. So put together, this is life. And this is the 7, this 7, just 7 Chinese character. This is 10. So put together the 70. And this means old. We call ko or old. And this is actually come and go and come. But in this case, from. So put together, we have from old days. And this, it means seldom. So that a translation goes this way, man seldom lived to be 70 years old. So why not celebrate people who got to 70s? And I happened to find a dictionary, Japanese English dictionary. 70 is the age of man. This is son. I'm not sure, I don't know about the Bible at all, so that, but anyway, I found this in my own small dictionary, Japanese English dictionary. Okay, so yeah, I just find a picture, a friendship of 20 years. This is my office. just after the IFAC Symposium 1997, Kyoto University. Sergio was 50, and I was 45. Giorgio is also 55. Okay, thank you very much.